Hello again. This is the last lecture in week 9, and it's the last lecture on confidence intervals. And this one is on confidence intervals on the variance. And this one does not follow our usual form, which we've seen already, something plus or minus something times something. For the variance, it's quite different. We're making use of the fact that the quantity n minus 1 sx squared divided by sigma x squared is chi-squared distributed and has a distribution that looks like this. So this quantity, n minus 1 sx squared over sigma x squared, is equal to a sum of almost standard normals. And as we mentioned in an earlier lecture, this tends to a chi-squared distribution, and with n minus 1 degrees of freedom. If I draw that distribution, I see something like this. It looks a lot like a log normal distribution. It starts at 0. It can't be negative because the sum of these terms, sum of squared terms cannot be negative. It's going to be positive. So it has this non-negative shape skewed to the right, and then we can look up values along the horizontal axis that have areas associated with them. So for example, chi-squared subscript alpha by 2 with new degrees of freedom will be that point along this axis with area to the right of it of alpha by 2. And these values will come from the last table in our summary pages, the chi-squared table. There's a symmetric value, or not exactly symmetric, but a value at the other end, chi-squared 1 minus alpha by 2 with new degrees of freedom, having area above it of 1 minus alpha by 2, and that means area below it of alpha by 2. So these 2 points together have area between them of 1 minus alpha. Area below this is alpha by 2, area above this is alpha by 2, so the area outside is alpha, so the area inside is alpha. That means we can write this probability shown in this picture as follows. The probability that our chi-squared distributed random variable, which is this thing, n1 minus 1 s squared over sigma squared, it lies between these two numbers must be equal to 1 minus alpha. And all we need to do now is, we substitute in what chi-squared equals, and now we just have to manipulate this so we get a sigma x squared in the middle. And once I've rearranged that, I'll see something like this. Probably that n minus 1 sx squared over chi-squared alpha by 2 with n minus 1 degrees of freedom is less than or equal to sigma x squared is less than or equal to n minus 1 sx squared over chi-squared 1 minus alpha by 2 with n minus 1 degrees of freedom. And this whole probability must be equal to 1 minus alpha. So these terms here, on the left-hand side, this has to be our L, and this has to be our U. So the probability that our true variance lies between L and U is just 1 minus alpha. And that means our LU has this form for variance. It's basically, it's 2 terms, one involving chi-squared alpha by 2, and the other involving chi-squared 1 minus alpha by 2. So we'll illustrate this with an example. If we refer to example 6.5, which is another one in the series of the iron core permeabilities, the question is, what is the 95% confidence interval on our estimated variance of the iron core permeability? So 6.3 was the original one, and there we had assumed that the true variance was known to be 225. Example 6.5, we then said, well, if we didn't, suppose we didn't know the true variance, but we had estimated it to be 225, then sx squared is 225. And now I'm asking, what is the 95% confidence on the true variance, sigma x squared, if this is the information that I have? I've taken 25 samples. X bar, which doesn't enter into this problem, is 960, and sx squared, which does enter into this problem, is 225. So from above, we see LU has this form here. So I just plug in the numbers, 25 minus 1 times the sx squared, which is 225, and same thing on the right-hand side. So I just need to figure out what these two quantities are here. Chi-squared alpha by 2, so this is the point along the horizontal axis with area above it of alpha by 2 with 24 degrees of freedom. And this chi-squared 1 minus alpha by 2 with area will be that point with area below it of alpha by 2. We're asking for a 95% confidence interval, so alpha is 1 minus 0.95, which is 0.05. And our chi-squared tables tell us the following. 1 minus alpha by 2, 24 degrees of freedom. Alpha by 2 is 0.025, so 1 minus alpha by 2 is 0.975. 24, this gives me 12.40 from the chi-squared table. And chi-squared alpha by 2, which is chi-squared 0.025 with 24 degrees of freedom, is 39.36. And now all I have to do is plug these numbers into my confidence intervals, and I get that the confidence interval on the true variance is between 137 and 435. We see that this is actually a pretty wide confidence interval. It's about a factor of 4 different. We have two things. We have to remember that this confidence interval on variance, and it's a squared quantity. But the other thing is variance is always harder to estimate than the mean. So there'll be more uncertainty associated with variance, and so its confidence intervals will always be larger. The confidence interval, if I wanted the confidence interval on the standard deviation, all I have to do is take the square root of these two numbers. Okay, so the 95% confidence interval on sigma x is just the square root of this thing here. And that's basically 11 to 20. So now this changes by about a factor of 2. And that's more sort of intuitively understandable. I should probably try to show you where I got those these chi-squared values from the summary pages. So let me just go back out here. Okay, oh here, there's the chi-squared distribution right there. And so what did we have? We had 24 degrees of freedom, which is right there. And we're looking for the point with 0.975 above it, and that was 12.40. So that's what we came up with in our example that we just looked at. And then with 24 degrees of freedom, we're looking for the point with 0.05, so 5% area above it, and that's 36.42, and that's the value that was in the example. Let me go back to the example to show you that. Yeah, so the point with area to the right of 0.975 was 12.4, and the point with the area to the right, oh, I got the wrong one here, is 0.025, so I picked the wrong one. Let's look again here. 0.025 is this one at 24 is 39.36. Okay, and that's what we just saw in this picture here. Okay. Well, that concludes our lectures about confidence intervals. A fair amount packed in here, but I think if you remember the general form for two-sided confidence intervals for means and proportions is something plus or minus something that's something, then it's really just a matter of filling in the blanks. The only one that you really have to remember then is the one for confidence interval on variance. It is a different form entirely. This is this. Let me just see if this is. Confidence intervals. Here we go. So this is in the summary pages. There it is, right there. By the way, in the summary pages, there's also confidence interval on ratios of variances, but we're not looking at that in this course. So we go as far down as this, and there is that confidence interval. Okay, so you don't even have to remember that formula. Okay, that's it for this week. After this, I guess you're headed into a fall break. I hope it is enjoyable, and that you manage to get caught up wherever you need to, but also have a bit of fun. Okay? See you later.